Hello there, welcome back. Hope you are doing very good. So in this video, we'll prove a very useful commutative relation between spin operators, and this is a relation that you'll encounter very often when you are dealing with spin in quantum mechanics. So we'll prove that the commutator between the s squared operator and the sz operator, it vanishes. So it's equal to 0. And similar is the case for sy or sx instead of the sz operator. So s squared with sy or s squared with sx, it vanishes. So let's start proving it. So in this context, the s squared operator, it's defined as sx operator squared plus sy operator squared plus sz squared. So it can be thought of as a square of the total spin angular momentum. So while proving this relation, we'll use the fundamental commutation relations between the spin operators sx, sy and sz, and those fundamental commutation relations, they read sx with sy, that is equal to iota h bar sz, and all the cyclic permutations, and I'll write it out explicitly, sy with sz, that is iota h bar sx, and sz with sx sy. So these are the fundamental commutation relations that the spin angular momentum obey, and these are the relations that any form of angular momentum obey, be it orbital angular momentum. So the orbital angular momentum Lx, Ly, Lz, they also obey the same relations. So any form of angular momentum has to obey these fundamental relations. And there is one other fact about the commutation relations for the spin operators that we'll use, and that is that the commutator of Sx with itself, it vanishes. And it's a very obvious fact because as you can see that as Sx commutator, that could be written as Sx minus Sx, so that would be Sx squared minus Sx squared, so it simply vanishes. And same is the case for Sy commutator with itself and Sz commutator with itself. The commutator with itself, it vanishes. And more precisely, what we are going to use is that the commutator of any power of Sx, say Sx raised to a power of n, with Sx, that vanishes. Because Sx commutes with itself, so any power of it also commutes with Sx. And this is also a very obvious thing because as you can see that this commutator on the left can be written as Sx to the n, Sx minus Sx to the n. So I could write it as Sx to the n plus 1 minus Sx to the 1 plus n, and this is the same as, so this simply vanishes. And similar is the case for Sy and Sz operators, that Sy to the power of n, any power, commutes with Sy, and Sz of any power commutes with Sz. So these are the facts about the commutation relations for the spin operator Sx, Sy and Sz that we'll use while proving this relation. So let's start proving this relation, that the commutator of s squared with Sz, that is equal to 0. So let's start considering this commutator on the left, s squared with Sz. So s squared could be written as Sx squared plus Sy squared plus Sz squared with Sz operator. Now we'll use one property of the commutators in quantum mechanics. So that is the additivity property. So the commutator of sum of two operators with another operator is the sum of the commutators, A with C and B with C. So by using this property, I can reduce this commutator, I can expand this commutator rather. I can expand it as Sx squared with Sz plus Sy squared with Sz, Sz squared with Sz. Now the third commutator here, as you can see, it's the second power of Sz with Sz, and as we just saw a couple of minutes ago that this commutator is equal to 0. So this commutator Sz squared with Sz, it vanishes. So we are just left with Sx squared with Sz plus Sy squared with Sz. And here we can use another property of the commutators, and that property is a chain rule. So the commutator of product of two operators, it can be expanded as A commutator of B with C plus commutator of A with C post multiplied by B, and this order cannot be fidgeted with. So if you take out A, it has to come to the left as here because it is multiplied with B from the left, and if you take out B, it has to come out to the right because it is multiplied with A from the right. So this, if you fidget with this order, it's simply wrong. So we can use it to simplify this expression. So I could write it as Sx squared as Sx, Sx, Sz plus Sy, Sy with Sz. And now if I lift these as A, B and C, so this as A, this as B and this as C, I could use this formula. Now I can use this formula and I can simplify this first commutator as, so I can write it as A, which is Sx commutator with B and C, Sx, Sz, plus commutator of A with C post multiplied by B, that is. So this is the first commutator here, and similarly I can expand the second commutator here. So I can write it as Sy, Sy Sz plus Sy Sz, Sy. So from here, what we can see is that we need the commutation relation between Sx and Sz and the commutation relation between Sy and Sz. And this is what we can use, we can directly take from our fundamental commutation relations that we wrote in the beginning. So these fundamental commutation relations. So we need the commutation relation between Sx and Sz. So we can take it from here. We use one of the properties of the commutator, that the commutator between A, B is equal to negative of commutator of B and A. So the commutator of Sx with Sz here, this is equal to negative of I h bar Sy. So negative of the commutator of Sz with Sx. So I can write it as the commutator of Sx and Sz. So I write here again. So we now have this expression, and we can substitute for the commutator of Sx and Sz from the fundamental commutation relations here. So Sx Sz commutator, that is negative of Sz Sx commutator, so it is minus I h bar Sy. So in the first two terms I can write it as Sx minus I h bar Sy plus again here minus I h bar Sy Sx. And in the last two terms, the commutator of Sy and Sz, that is equal to iota h bar Sx. So that I can substitute here. So I am left with Sy. The commutator here is minus I h bar Sx. And here again the commutator is plus. It's plus I h bar Sx. And here again the commutator is plus I h bar Sx with Sy. And I take this relation simply from here. Sy with Sz is I h bar Sx. And now as I can see that minus I h bar, it's just a complex number, so I can take it out of the whole thing. So I'm left with Sx, Sy, keeping track of the order. This is with a negative sign, minus Sy, Sx, plus keeping track of the sign. This is Sy, Sx, plus with the order Sx, Sy. And now as you can see that although you know that Sx, Sy and Sy, Sx, they don't cancel because they have a non-zero commutator, but Sx, Sy cancels with negative of Sx, Sy, it cancels with the positive of Sx, Sy. So that is why these two terms, they cancel among each other. And again, this is the similar is the case for Sy and Sx. So these two terms, the positive and negative, they also cancel each other here. So I am left with minus I h bar multiplied with a 0. So in all, I'm left with a 0. So that's how I have proved here successfully that the commutator of s squared operator with sz operator, that is equal to 0. And exactly the similar route can be taken to prove that the commutator of s squared with sy or s squared with sx is 0. And this is because of the fact that the operator s squared here, that is symmetric in s squared, sy or sz. So you can use the fundamental commutation relations and some properties of the commutator, and you can prove exactly in the same manner that s squared and sy or s squared and sx, they also commute. So this is how we prove this very useful relation, and it's a useful expression because now you can say that s squared, let's say s squared and sx, they can be diagonalized simultaneously, and they have simultaneous eigenvectors. So this is something that we prove that we use while dealing with spin in quantum mechanics. So this is an important relation. And one more thing that I want to point out here is that similar expressions, they obey for the orbital angular momentum operators L squared, Lz, Lx, and Ly. So L squared, that commutes with Lz operator, that is because of the fact that, as I mentioned in the beginning, that Lx, Ly, or Lz, they also obey exactly the same fundamental commutation relations, because orbital angular momentum is also a form of angular momentum. So this is it for this video. If you have any questions or comments, you can write to me in the comment section. I'd be happy to address those. And hope you like the video. Please don't forget to like the video and subscribe for the channel. Thanks for watching. See you next time. Bye bye.